Hi, Assalamualaikum and good day. Today we are going to learn more on the analysis of functions. Today's session is a continuation of our last session on analysis of functions. If you recall, in the last sessions, we have learned on how to identify the interval where the function is increase, decrease, concave upward, and concave downward. And we also have learned on how to determine the extremum points of the given functions, which is either maximum, minimum, or inflection points. So today, we will continue with sketching the graph of polynomials and rational functions. Basically, the information on the x and y-intercept, increasing and decreasing interval, concavity, extremum points, and asymptotes are very useful in sketching the graph of a function. The following procedures give a systematic method of compiling this useful information through curve sketching. When sketching the graph of a polynomial, the following information are useful: x and y-intercept, maximum and minimum points, and inflection points. Refer to example 10. Given a polynomial function in which you need to find those information and finally sketch the graph. First, you need to find the x and y-intercept. X-intercept is obtained by solving fx equal to 0, in which y is equal to 0. By solving fx equal to 0 and simplify, you should get two x-intercept, which are 0, 0 and 4, 0. Y-intercept is obtained by solving f0. Here, x is equal to 0. Substitute into the function and simplify, you should get 1 y-intercept, which is 0, 0. Next is to find the critical points in which you need to solve f prime x equal to 0. By solving f prime x equal to 0, you will obtain x equal to 0 and x equal to 3. Substitute this value into the function, you will get the corresponding y values. Therefore, the critical points for the given functions are 0, 0 and 3, negative 27. To find the increasing or decreasing interval, you need to apply the first derivative test. If f prime x less than 0, you should get decreasing interval. And if f prime x greater than 0, you will get increasing interval. Here, we are using x equal to 0 and x equal to 3 as the cutting point of the interval. From the first derivative test, fx is increasing on the interval 3 to infinity and decreasing on the intervals negative infinity to 0 and 0 to 3. From the table of f prime x, there is no extremum point at point x equal to 0, as there is no changes of sign. However, fx is minimum at point x equal to 3, in which 3 negative 27 is the minimum point. To determine the concavity of the function, you need to apply the second derivative test. If f double prime x is less than 0, the function is said to be concave downward. If f double prime x is greater than 0, the function is said to be concave upward. By solving f double prime x equal to 0, you will obtain x equal to 0 and x equal to 2. These 2 points are used as the cutting points of the interval. From the second derivative test, the function fx is concave upward on the interval -infinity to 0 and 2 to infinity, and concave downward on the interval 0 to 2. As the concavity changes within the interval, there are two inflection points. By substituting x equal to 0 and x equal to 2 into the fx, you will get the corresponding y value. Therefore, the inflection points for the given functions are 0, 0 and 2, -16. Finally, combine all the information obtained from A to F on the xy plane and sketch the graph. X-intercept at point 0, 0 and 4, 0. Y-intercept at point 0, 0. Minimum point at point 3, -27. Inflection point at point 0, 0 and 2, -16. Then combine these 3 points accordingly using the correct shape of graph. When sketching the graph of a rational function, besides the x and the y-intercept, maximum and minimum points, and inflection points, we also need to identify the vertical and horizontal asymptotes, if any. To find the vertical asymptote, let the denominator qx equal to 0. Refer to the first example, fx equal to 5 over 3x minus 6. By letting 3x minus 6 equal to 0 and simplify, you should obtain x equal to 2. Therefore, the vertical asymptote for the given function is at x equal to 2. For the second example, fx equal to x plus 3 over x squared plus 9. By letting x squared plus 9 equal to 0 and simplify, you will notice that x is undefined. As the denominator has no zeros, the vertical asymptote for the given function does not exist. To find the horizontal asymptote, you need to refer to the degree of both numerator px and denominator qx. Degree here refers to the highest power. If the degree of p is less than q, then y equal to 0 is the horizontal asymptote. If the degree of p is equal to q, then the horizontal asymptote is found by dividing the leading terms. If the degree of p is greater than q, then there is no horizontal asymptote. Refer to example 1, fx equal to x plus 3 over x squared plus 9. As the degree of p is 1 and the degree of q is 2, p is less than q. Therefore, the horizontal asymptote for this function is at y equal to 0. For example 2, fx equal to x squared plus 3x plus 1 over 4x squared minus 9. As both numerator and denominator having the same degree, which is 2, divide the leading terms. X squared over 4x squared is equal to 1 over 4. Therefore, the horizontal asymptote for this function is at y equal to 1 over 4. Now, refer to example 11. Given a rational function in which you need to find those information and finally sketch the graph. To find the x-intercept, you need to solve fx equal to 0, in which y is 0. By solving fx equal to 0 and simplify, you will get one y-intercept, which is 0, 0. Y-intercept is obtained by solving f0. Here x is equal to 0. Substitute into the function and simplify, you will get one y-intercept which is also 0, 0. Next is to find the vertical and horizontal asymptote. To find the vertical asymptote, let the denominator qx equal to 0 by letting x minus 2 equal to 0 and simplify, x is equal to 2. Therefore, the vertical asymptote is at x equal to 2. To find the horizontal asymptote, refer to the degree of both numerator and denominator. As both numerator and denominator having the same degree, which is 1, divide the leading terms. 5x over x is equal to 5. Therefore, the horizontal asymptote is at y equal to 5. To find the increasing or decreasing interval, you need to apply the first derivative test. As given a rational function, you need to differentiate the fx using quotient rule, which is f prime x equal to v u prime minus u v prime over v squared. You will obtain f prime x equal to negative 10 over x minus 2 with the square. By letting f prime x equal to 0 and simplify, you will notice that x is undefined, meaning there is no critical point for the given function. Therefore, there is no extremum points. Even though there is no critical points, you still need to investigate the behavior of the curve at the vertical asymptote x equal to 2. From the first derivative test, fx is decreased on both interval negative infinity to 2 and 2 to infinity. To determine the concavity of the function, you need to apply the second derivative test. By solving f double prime x equal to 0, you will notice that x is undefined, meaning there is no inflection point. By taking x equal to 2 as the cutting point of the interval from the second derivative test, the function fx is concave upward on the interval 2 to infinity and concave downward on the interval negative infinity to 2. Finally, combine all the information obtained on the xy plane and sketch the graph. X and y-intercept are both at point 0, 0, vertical asymptote at x equal to 2, and horizontal asymptote at y equal to 5. You should be able to obtain the following graph. In order to check your understanding on today's lesson, please do the following question. In the next lesson, you are going to learn on how to solve the maximum and minimum values problem. So,